kind of architects, we often like to build tools, and that extends to our classrooms. And so this is, I know, a favorite of many people, is to see what tools we're using. So we have 4 of those, and a lot of them seem to be focusing on different types of visualization for architects. So we have a bit of we sometimes sit at a invisible layer in the, or seemingly invisible layer in the system, but that can be challenging for our students to engage with, especially when they're younger. So we have some visualization papers, and also the challenge of being able to test projects and appreciate that very important aspect. So I guess without further ado, can we let's see, can we have our first presentation? That would be RIPES, and is Morten here?
Yeah, if you can hear me.
I can hear you.
Am I audible? Perfect. Okay, great. And you can see my presentation as well.
Yes, I can.
Great. Okay, so I'll just go ahead. Yeah, so my name is Morten, and I'll be talking about RIPES, which is a visual computer architecture simulator built around the RISC-V instruction set. So the simulator is targeted towards educational use and has many of these visualization aspects, and actually tries to visualize as much as possible. One of the main key points is to visualize different data paths during execution of a program that the user provides. The program can simulate, the application simulates various in-order architectures, going from like just a single cycle to a 5-stage pipeline, and some intermediary designs in between, to pretty much follow the curriculum that someone would go through when they're following a classic book on computer architecture, at least an introductory book. To support this, there's also a built-in assembler, there's compiler support, so you can write C programs and simulate those. There's cache simulation, as well as memory mapped I/O. So all of these different sort of layers of abstraction provides you a method to either see the sort of very low details, the cycle-to-cycle details of your pipeline, and go all the way through the hierarchy up to like seeing external effects on memory mapped I/O, for instance. So many of these things or features are not necessarily new, but I think the value in the project really lies in rethinking and redoing what has already been available across many other older simulators in sort of a fragmented tool space, but to merge all of this into an active open source project and a coherent project. So a bit about the application itself. It started in 2016 as just an instruction set simulator. And since then, as far as I'm aware of, tens of universities use it in their teaching. It's a bit hard to track. And in terms of its open sourceness, on GitHub, there's over 600 stars and almost 100 forks. So there's also a bit of interest here in the open source community. But to get a feel for the application, let's just go through some of the features here. So this is where you would write your code. To the left-hand side, you have your source code where you can write assembly or C code. And then to the right-hand side, you see the disassembled view. Overlaid here, you see highlighting of pipeline stages. This is the instructions that are present in different pipeline stages during execution. And this provides a visualization of instruction level parallelism, really. Now going on to the process of visualization, this is what you would see. The selected processor here is a six-stage dual issue model. And as you can see, above stages, we highlight which instructions are in the different stages, where their stage has been flushed and so forth. And also you can see where multiplexers are getting their operands from and things like this. So really to get a sense about what is actually happening inside the data path during execution. And this is an example of the cache simulation tab. So to the right here, you see a cache visualization, as well as a visualization of how you're indexing into a cache. Up here, you can configure your cache in terms of geometry and policies. And down here, you see a cache statistics view that updates while you're actually simulating your program. So you can get a real-time sense of where different places in your program show good or bad cache behavior. So yeah, that is RIPES in a very brief nutshell. And briefly on future work, I think they're still missing branch prediction to really have the application be a good companion all throughout an introductory course on computer architecture. And then support for the RISC-V, 64 and 128-bit instruction set variants. Now, this is already in the work, so I don't think it will be too soon before this is out. And then also some more advanced concepts like out-of-order processors. This is just a bit difficult because we don't really have the entire sort of teaching sphere having converged on a single design as we have with, you know, the classic 5-stage pipeline. There's many different out-of-order designs and many different design choices here. So it's a bit hard to choose what goes into the application itself, but it could be cool if we have some good visualization of this as well. And then also in RIPES, things are like circuits are defined in a custom domain-specific hardware description language called VSRTL. But this isn't, I mean, it's not really future-proof, and it would be nice if we could hook into many of the new tools in the hardware compilation open source space and provide this method of visual simulation of digital circuits, and but then use this paradigm for, you know, circuits described in VHDL or Verilog and so forth. So that's a bit for the future. So RIPES is on GitHub, and there's pre-built binaries there if you're interested. And if you have a question for me, you can ask them in the session afterwards or send me an email. Thank you.
Thank you, Morten. So next we have using Logisim for teaching data path and control. Mehmet, are you there? I see. Can you share your screen? Mehmet, are you there? Uh-oh. So we seem to have lost, temporarily, I hope, lost a participant. Perhaps we can go on to the third presentation. That would be a framework for microarchitectural traces and abstraction layer in computer architecture education. So Stefan, would you take it away?
Yes, thank you very much. Thanks a lot for having the opportunity to talk here today. I'm professor at the Munich University of Applied Sciences in Germany, and some of you may know me as the director of the Free and Open Source Silicon Foundation and member of the board of directors of the RISC-V Foundation. So you're not really surprised probably about some of the content I'm presenting. I got professor 2.5 years ago, and I brought into the game all the experience I have around open source silicon and RISC-V, and I was very enthusiastic about teaching now computer architecture to students. And I know there's all those great open source EDA tools, in particular Verilator, which I love a lot. And I thought this is like a made game, like this very, very great opportunities. What turned out for me, because I'm in computer science faculty, the students that I'm facing, especially at my universities, they have a very, very fundamental, very rough understanding about digital design. So getting into RTL is out of the play for me. So what I'm using is tools exactly like RIPES. We start the first 2 to 3 weeks with RIPES. They learn a little bit about the assembly, 5-stage pipeline, etc. But I really want to get onto the course, and this is in particular, like maybe I can actually follow up to what Morten said. At some point, I want to get away from the models and want students to experience what an actual processor looks like. And there's many corner cases and many interesting optimizations that you're not really teaching, but they find very valuable. But I found now this semester, especially if you have a lab assignment, that they discover like what non-blocking loads mean and how you can optimize around. This is stuff I really find interesting, and they find interesting if presented the right way. The wrong way I found very, very quickly was waveforms. So they don't really like waveforms. I love waveforms. Bad combination. So I thought about different ways of presenting it, and I came up with a framework. I've iterated a little bit, and I'm converging now to how it looks. It's kind of split into 3 different stages. The one is like RTL simulation of actual open source processor cores. They are all RISC-V cores at the moment. Of different complexities, starting from like simple microcontrollers up to out-of-order machines, right? Work in progress, like not very advanced. There's one example running on FPGAs too. In future, it would be interesting, but the main tooling I use is around RTL simulation. So the students get pre-compiled simulations from me, and they develop software on it and do micro benchmarking to understand microarchitectural effects. So that's the goal here. I want to abstract from digital signals. I want to present to them the microarchitectural effects. For example, how does an instruction traverse the pipeline? What does the branch predictor say? How is it updated? And those kind of information that are very important to us, right? And then there's a CTF trace, which is a standardized trace format that you can read with multiple tools. It's stored for each of those runs, and then they can do some post-processing on it. And I have a tool that I called Pipeline Viewer. It's a Python tool that is a little bit inspired by the Gem 5 out-of-order pipe viewer. If some of you are familiar, it also comes with the Boon. But it's more sophisticated. It has different features supporting all those different microarchitectural details that I want to cover. So how do I do this now? That was the biggest challenge, of course. And as an open source person, I try to not fork everything, right? So it's important for me that I can use the cores as they are and can just tap in, right? And System Verilog has a very interesting feature for this, right? This is the bind feature. I hope some of you are familiar with it. It's usually used for verification tasks, and you can just tap into a design top level by its hierarchical name, and you can bind it to your module, and it's sitting on the outside. So you can keep the original code. I run the original test benches, and then I use my trace logic to observe the control and also trace relevant data that might be of importance, like program counters are important at some point in time, and the decoded instruction, for example. And beyond that, it's more about the control signals and handshaking that I track in the pipeline. Then it traverses immediately to C++, essentially, to do all the processing, the post-processing for the microarchitecture in DPI. And then I generate those raw events, which are then stored in this trace format. So what you use in the end is Pipeline Viewer. Those of you not familiar, it's kind of like how you would put it on a slide, but in ASCII. So it's colored ASCII, as you can see. I find it more useful for the students as a tool. It also makes me a little bit independent about their computers. So this is, in this case, a 9-stage pipeline, and you can see instructions from top to bottom. Unfortunately, it's cut off. I took it from the paper. I didn't really take the right one for the presentation. But you can see, like, there's more information on the right. There could be like a branch predictor update, etc. There's the instruction, there's a program counter, etc. You can configure the format of the output. You can change the width of the pipeline view, and what you can see is like it's a window that wraps around, and you can see how the instructions towards the pipeline. You can do IPC analysis on it and understand how, for example, dependencies influence, in this case, the Superscalar tool, the execution. So currently I have IBEX and Swerve EL2 and Swerve EH1 are the ones that I currently have on GitHub. I have to polish a bit because I changed it this year again a little bit. I have to do the former Ariane and the Risky core, which were from the Pulp team and are now part of the Open Hardware group. And yeah, Boom is something I did previously. I do some text to trace processing. I want to tap into Shipyard to do it properly. If you're interested for your core, just get in touch. It's much easier if you know the core. This is something I can say. It's rather complex for those cores already to find the necessary information, and I work with those teams to get it. This is where you can find it on GitHub. You can get me on Twitter or just send me an email, which is the easiest one, or just ask questions. Thank you very much.
Thank you, Stefan. So perhaps if Mehmet is there, can we go back to using Logisim for teaching data path and control?
Can you hear me?
I can hear you.
Thank you. Okay. So how do I share my screen?
I think there's usually on the bottom bar, there's a share screen with a green box with an arrow pointing up.
Yeah, I don't see it.
So do we have our tech support here who might be able to help out with that?
Well, one thing I can say is that if you're in the web browser interface, you see a different orientation of the screen than you do in the regular Zoom interface. If you have trouble with that, I can send you the link to the regular Zoom interface, and then you can pop out after the next talk, maybe you can come back in and then do yours last.
Sure.
So let me do that.
Okay, so then we'll move on to improved processor design, project testing, and I believe Ryan is ready to go. Are you there, Ryan?
Yep. Can everyone
Okay.
hear me?
I can hear you and I can see your screen.
Okay, so yeah, I'm here to present our flow for improved processor design project testing. It was developed by myself, Connor, Dan, and Bora. So Connor and I are graduate students at Berkeley, and then Dan and Bora were the professors in the course this flow was developed for. Okay, so the goals of this project were to increase the realism of graphically based processor design projects. So we wanted to create a better link between like Logisim blocks and the physical ramifications of that design. It's very easy to become decoupled from architectural decisions and what it actually corresponds to in the real world. This was integrated in the project that we do with the introductory machine structures course that has a component on computer architecture and ISAs. And the project implements the data path shown on the right of the screen. It's a two-stage RISC-V processor. So we wanted to measure the performance of these student processors against the standard RISC-V ISA tests and generate some synthesis metrics such as the longest path score or an approximate for area. We also wanted to build this flow in open source tools because we have about 2,000 students in the course and we can't afford 2,000 licenses. So we needed to make sure it could be auto-graded easily and at scale. And then for reference, we used to test designs using Python and the TTY mode in Logisim. It's just very slow, first off, but it also made us write our own tests, which had to be simple due to the number of tests we had to write. And then it relied on comparing the status of specific exposed registers, which opened up some holes for flaws in the testing. So this is the overall backend flow we created. The entire thing is built on the open source tools. So we do some simulation using Verilator, synthesis using Yosis, and then we use MOS for similarity checking. And I'll break down the different phases of this flow over the next couple of slides. The first phase is HDL emission, where we convert student designs in Logisim into Verilog. So this harnesses a feature in Logisim Evolution, which is a fork of Logisim. It's called FPGA Commander. And then we have to make some custom modifications because we're obviously not targeting real FPGAs. We also check for some common errors that are introduced in Logisim, sort of non-idealities. We correct those, and then this gives us Verilog that corresponds to a student's circuit that they had drawn. After that, we generate what we call correctness scores. So this is the simulation aspect. So we pair a student CPU with a simple Verilog memory model and a CSR shadow model. What that does is it handles operations for two hosts. The CSR that the ISA tests rely on. We use a shadow model because when asking students to implement CSRs in an introductory computer science course, it led to a lot of confusion and just general, incorrectness that wasn't worth having to go through with students versus the overall concepts we wanted them to learn. So then we built this core module into a simulator and use it to run the standard ISA tests, and that produces an output like is shown in the bottom on that kind of black terminal printout. The next phase is design scores. So this is like our synthesis metrics component. So we take a student's design, we pass it through a simple Yosis run, and we can generate a technology-independent gate list. For ease of comparability, we just restrict the type of gates to be NOTs, NANDs, and flip-flops, so 3 basic gates. And then we can generate some proxy design scores. So for area, we multiply the type of cells by the transistors per cell and sum them together. And that gives a proxy of how much area that is being used. And then to generate a timing approximate, we generate the longest topological path between two state elements in a given student's design. Next, we do similarity scores. So just briefly, we take student emissions of Verilog, we aggregate them, and then can submit them to MOS. It does still require a lot of human insight because these are highly modular designs, which leads to a lot of similarity. So you really have to sift through false positives, but it does enable us to do this comparison, which wasn't possible before with the way Logisim stores files. So quickly, it wants to load. Okay, so this is just run through the flow. So I'm just showing here that, there's nothing existing. You just execute make. So right now it just finished emitting. So now there's Verilog. It's building the simulator. Now it's running all the ISA tests. And now it's running Yosis. So Yosis is the longest part of this entire flow, but even then the flow end to end is on the order of like a minute or two, which is significantly faster than running Logisim-based tests. So now Yosis is finished and it prints out the different metrics. The rest of this is kind of me just showing the output files, but I'll go here and just show this is some of the Verilog that's emitted. It's very intractable, so it's not really designed to be easily read, but it is a direct correlation to a student's graphical design. Okay, there we go. So we use this in the fall 2020 iteration of our course. There was no degradation in student performance, even though they are running against much more rigorous tests. And then anecdotally, there's a lot of interest around what we call those design scores. So a lot of things about, how do I design my processor to be efficient rather than, oh, I just want to pass these tests and get it over with. So that was something that was nice and led to a lot of interesting questions. And then the conclusion, so there's a downside. It's very difficult to maintain Logisim to Verilog emission. It's pretty buggy. Logisim is a little intractable to debug, but we bashed a lot of bugs early on in the semester, and as it gets more stable, it should go better. Future directions, it would be nice to synthesize to something like Sky 130 or ASAP 7, so then you can get real performance metrics and not just gate counts, and also to allow students to at least run synthesis locally so that they can kind of iterate on their own instead of relying on our autograder. And outside of 61C, our flow is very generic. We enter it with or without Logisim. You can just take whatever components you need or you want. So if anyone is interested in, any single component, feel free to reach out via email. And that is all I have.
Thank you. Thank you, Ryan. And let's see, Mehmet, are you there?
I hope you can hear me now.
I can hear you. I can see you too.
And my screen?
Yes.
Yes, there we go.
Right, great. Finally. So we have been teaching data path and control by doing textbook figures and hand-drawn pictures like the one on the bottom. And the problem with this is it's one thing, it looks easy when the professor is doing the drawing, so they perceive it as simple, but then when they have to do it, it's a difficult task. And when it's hand drawn, it's there's a lot of erasing, redrawing, so it's really difficult to see what's happening when you take a submission, and it's really challenging to grade. So we prefer using drawing softwares to make it more precise, but it's time consuming and tedious. Also, not that easier to grade. And the grading is the main problem, not because it's too much work, but because it doesn't give quick feedback to anybody, not to the grader, not to the students, and sometimes incorrect feedback happens. These are difficult to grade, and that is worse than giving no feedback at all. And giving slow feedback, just returning the assignment in a week, in 10 days, it's not much better than giving no feedback at all, because by that time they're already over it and they don't remember what they did. So we turn to tools that are available, and there was some convergence in versions in Logisim. So now we have this Logisim Evolution that is being used by a couple of universities. So we ended up with circuits like these. So this one is simulating the execution of an ARM v8 data path, and the circles that you're seeing on the control unit are showing you the exact instruction that is flowing through the data path. So we've got quite a few 2 dozens or so instructions implemented, and that allowed us to do a great many deals of things with this. So the benefit of this is, you know, this course is an early course, and it is a prerequisite for a later embedded development and programmable logic course. So they're going to take some HDL classes in the future, and they're going to get better at writing software by then. So we try to stick with visual design and visual simulation for this course in order to minimize that amount of prerequisites. So this is easier than using some drawing software, but still kind of tedious and slow. But what does, it gives instant feedback. So you any simple misconnection, you instantly see it, and you can do mini unit tests by setting the state and toggling the clock, so you see how it progresses throughout the circuit. And you can do, you know, larger simulations by using regular assembly programming, regular development tools, and then finally loading the result into the Logisim circuit. More importantly, they can visualize how a data path works and how control is implemented. So they can actually see the wires lighting up and down. And this is, you know, seeing the state changes, seeing register memory content changes, and they can really go down in the layers of abstraction to see how everything works. So the way we started out was to just use this for control and data path, but then it slowly reached to every aspect of the course. So now we use it for review of digital logic design topics, you know, review of combinational, sequential, synchronous circuits. What is propagation delay? How do you determine critical path for a given circuit? What is the minimum period? What is the maximum clock frequency, and so on? And we revisit some of the issues that are not dealt with in the previous course, the tri-state buffers, multiplexers. How do you drive a wire from multiple places? How do you make sure only one of them drives at a time, and so on? So these are some example videos shared with students together with the circuit files, and they can see that you know, how combinational and sequential circuit differs in their operation, and how a synchronous circuit operates. The Logisim doesn't really give us all that nice of a timing simulation, but it can still help us visualize how the signal is propagated by using its iteration of the simulation. So if I iterate the simulation, I can see the blue dots showing me the updated wires. So using this, we can emphasize what is the minimum clock period. It needs to be, you know, greater than the critical path delay, and so on. We address tri-state buffers and their use in multiplexers, but then we do some more work before we start building a data path. One of them is comparing a combinational versus a pipelined multiplier. Pipelining is one of the very first topics in the Patterson and Hennessy hardware software interface textbook. So it's easy to, you know, while working on latency topics, to get this out of the way, to show, you know, what kind of benefits do you get by doing a pipeline design, and emphasize this dual aspect of performance, the latency versus throughput. Then we work our way up to a full data path, starting with an accumulator machine, then a register machine. Then we add an instruction register, an instruction memory, branching, data memory facilities. So they start with the circuit on the left, and they are given descriptions and depictions, and they build these circuits in Logisim most of the way. So we start with a little bit of a calculator machine with a few operations. Then we add more registers and a way to select source and destination operands. Then we you know, group all those signals into one unified signal and call it the instruction register. And then we provide a way to cycle through instructions in a given memory block. So that's our instruction memory. Then we add branching and data memory. So they end up with this. And this is entirely created by the students by the end of, I believe, the third lab assignment. So at that point, they can use this little JavaScript assembler to write their assembly code, translate it into machine code and download, and just click load image. The downloaded file is loaded into the instruction memory, and they just turn on the simulation and it runs. So once they did this little toy architecture, they move on to converting this into a data path that can execute ARMv8 instructions. So we gradually, through many iterations, we add more registers and more registers, and we add a register subcircuit to hide away all the details. Then about 6 or 7 iterations later, they end up with this, where this is a smaller version of the first data path that I showed that is capable of executing about 15 different instruction types. But at this point, they can simulate an example IO program, and these blocks, while hiding some of the details, they still have these LEDs on top of them to show what's going on inside. And this is all, basic Logisim, no additions, no plugins. And they have a register file, an ALU, and a memory controller. So the third section of the course is a physical lab, where they have a Raspberry Pi, a bare metal programming, and some input-output operations. And what we did with this course was replicate all of that inside Logisim, so we can do 2 tracks at once, one physical, one simulation. We ended up using the simulation due to COVID, but regular time we would use both of them. So after doing some LED blinking exercises that are connected to the GPIO, modeling the exact details of the Raspberry Pi, they move on to final most complex lab assignment, which is using an LCD module and sending output through the serial bus, which are then converted to the parallel interface of the LCD module. And eventually, after quite a while, they would see some characters outputted on the display. So this, this is pretty much the limitation of the Logisim, with about 3,000 components, and 15 minutes of execution, they can see this exercise to its end. So at this point, the clock rate drops to about 25 Hertz. The future work is to use the FPGA synthesis and download mechanisms of Logisim to sort of hand the simulation off to an FPGA and get it back again to be able to examine the circuit in sufficient detail while also having a faster simulation. So this is all available on GitHub, and the URL is on the slides. Thank you, and I can answer any questions you might have.
Thank you, Memo, that we finally got you on Zoom. So now I see there's a fairly vigorous set of questions beginning to crop up. I just want to make sure that we go back to some that may not have been answered. So I think this was for RIPES. David Harris, you were wondering kind of maybe what learning objectives RIPES is addressing in your course or the courses you're aware of. Martin, and perhaps maybe give a notion of the context where you see this being very valuable.
Yeah, so again, I don't teach. I just work on the simulator as a side project. Again, the context would be that it really serves as a companion to the computer organization and design, where you often see these images of, you know, the data path, and then there's a few instructions, but you know, written on top of the stages. But you as a student, you might want to try out other situations, some more complex programs, and it's in that kind of situation. And then also, you know, this is the reason for why we have the different processor models that have, you know, multiple stage processor models, but they don't have forwarding, or they don't have hazard detection and resolution implemented, so that people can see that, you know, I write a program, and unless I do some custom scheduling of those instructions, then, you know, the semantics are off. So those kinds of things. Yeah.
Thank you. And please, Dave, if you have follow-up questions or
yes. I think I was muted, but it's a really nice interface you have. But when I think about what students are likely to do, they need to see these waveforms a few times when they're learning. And then what I'd really like them to be able to do is figure out what the signals would be on their own. So I'm just kind of wrestling with when I would use the simulator in a class, when I would use the graphic visualizer, because they won't be using that in their professional life. They'll need to be able to predict values on their own. So kind of that jump pedagogically.
Yeah, definitely. I mean, this is all, I think Stefan also was in on this, where sort of the difference, when do you choose the waveform view and when do you choose a visualization view, right? And how do you make that jump in between? I think RIPES in its current state, it's very much just focused on a visualization, and just sort of, you know, when you see the data path for the first time, and when you're just encountering, you know, the concepts of pipelining, and at that point, you might not even be thinking about digital logic. And writing the things yourselves. But I agree that it would be ideal if we could then also export a trace, a waveform trace from a simulation, and then go in and actually look at the waveform. That's not possible right now, but hopefully in the future, with, you know, more elaborate changes to the underlying simulator, that would be possible. But in short, the current focus is on, you know, just the visual part and not so much the trace.
Maybe I can add too. So we are using it, and I think it's among the DLX simulators, it's the best one at the moment. It's also easy to extend a little bit if you need tweaks here and there. And I think it's really for the objective, like, to learn the real fundamentals in the beginning. I use it in the first 3 weeks, as I said, right? At some point you jump over to actual pipelines, right? I think it's a break a little bit for them, but I think we always started at DLX, right? So to get the fundamentals of pipelining, get the fundamentals of instruction scheduling and reordering, loop unrolling, those kind of things we do, right? We have lab assignments around, here's a sequence, find data hazards, optimize the code, rearrange a little bit. I think for those kind of things, it's really good, right? Not to jump too deep into things. So for me, they are coming out of, like, they learned RISC-V assembly on a pure ISS level before, right? For them, it's the first contact with the processor. And as I said, like, they're not digital engineers, so waveform is not their format, definitely.
Thank you. So I'm going to skip a little bit just to get some of the other presenters involved. So I think, David, you also had a question for Ryan about if students have difficulty debugging if something goes wrong. So this was in regard to the improved processor design testing project.
Yeah, so kind of to give a little more context on the project, the way it's set up is there's this portion of the project called the coverage score, where students are supposed to generate a suite of unit tests, right? The testing instructions, and we compare that against, you know, do they test and do they test or whatever. And that's all based in Logisim. So they write their unit tests. We have a couple scripts that make them into little Logisim scripts. Then you can step the clock and walk through them. And so even there, so that's a way to debug, right? And even there's a lot of complaints because debugging in Logisim is not great. It's very difficult. It relies a lot on, you know, tracing, basically manually tracing wires in a visual form instead of looking at waves. So, and then with this flow in the back end running the ISA test, the way that it's structured on Gradescope is there's a set of visible tests that students see before the deadline. So those are all basically the same level unit tests as they should be writing for themselves. And then after the submission deadline, it reveals a greater set of tests that correspond to the ISA tests, right? So there's 2 levels of rigor. There are 2 levels before and after the deadline. And the reason for that is to motivate writing your own tests. So I think that's a little more context on, why it's set up the way that it is, or why there's a disaggregation between the ISA tests and what students are actually looking at. But yes, in general, just debugging in LogicSim is something that students really complain about and something that we've tried to come up with better ways to do, but there are some limitations just in the way LogicSim represents logic.
Thank you, Ryan. Any follow-up questions on that?
Well, just the thought, we've wrestled with whether there's any way to avoid Verilog and Verilog simulation in the first course with digital design. And I've never found a satisfactory alternative to it yet. So it's interesting seeing these different approaches. But I hate having black boxes. And I also like to steer students towards tools that they're actually going to use in the real world. And that keeps bringing me back to HDL and an HDL simulator.
Yeah, so the other thing is this is technically not our first course in digital design. Technically, this is like before that. So we have a whole course that's called Introduction to Digital Design. This course, CS61C, is typically taken by first semester sophomores, and it's sort of like a hodgepodge of many different things that covers sort of the entire compute stack. So it's already very wide in scope. So it goes from like C, performance programming, basic architecture, basic digital design, caching, ECC parity, RAID, like all these things. So it's really trying to cram a lot in. And so that also motivates, let's keep Verilog for the true introduction to digital design, and let's just give them a way to kind of get acquainted with architecture concepts and get really familiar with the ISA now, so they can build upon that when they decide they'd like to do digital design as a real focus. And yeah, even though you can teach Verilog very quickly, just in the volume that there is in this course, it's already, a consistent feedback is this is already covering so much. Trying to throw another language in there, I think, would pose a big difficulty for some.
Okay.
I would also
Thank
dispute
you.
the argument, to be honest, because you have a specific job in mind, right, David? So my students, none of them get near hardware again in their life, right? It's essentially about teaching them how to write performance software, how to understand the effects of the architecture on your programs, right? So it's not really like, if it's not like the expectancy that this is their job, like most of them become app developers, I believe. So like they will never see Verilog, and the ones that I showed it, they were very scared, right? And teaching it just for I love technical details, but I see where it makes sense to abstract them away a little bit. I think that's my take. So I would argue if it's electrical engineering, definitely, but for my kind of cohort, I think it's not really the best approach.
Okay, so let's see. So we had a couple of questions for Mehmet as well. And I'm sorry, losing track a little bit of all of the questions coming in. So there's some question about from Stefan. Did you look into using Circuitverse as a alternative to LogicSim, I believe? So Mehmet, would you like to follow up with that?
Yeah, I did answer him saying that there are no memory blocks in there. I don't think, right?
Actually, they are, but
there are.
I think it's different. There's few drawbacks in using Circuitverse, but it has the advantage of this all online thing, right? Collaboration. Students can share the projects. You have the whole assignment flow where you can grade the assignments, which I found very useful now, right?
Yeah, it is promising, but the level of detail that we have been implementing, replicating real hardware, is not going to be in there anytime soon, it looks like. But if the collaboration thing seems promising enough, we might be able to we might be inclined to move some of those features into Circuitverse as well. And then the other question was, is there anything in between? Why do we go to all this low level stuff? We use QEMU emulation a lot. So when we're doing assembly exercises, sometimes in class, we use the same development environments running in Eclipse. You have the QEMU configured to emulate the program, and you hook up the GDB to it. So it's really nice to have all your debugging features, breakpoints inside this powerful IDE. But then when you want to see the low level stuff, what's happening underneath, the things that you can't see, right? So when you're doing MMIO, you're writing to a register and some magic happens, right? So that stuff we were able to replicate in Logisim for the viewing pleasure, I guess, right? So it's not for high efficiency debugging, but it's nice to demystify what's happening under the layers.
So, and there was maybe a kind of a similar question with that, because you kind of have this paired physical system as well as the Logisim. So were you using that in non-virtual, non-COVID times?
So we were using the real hardware. It's fairly cheap, so it's $100 all told. So students can purchase that and use it in future courses and projects. It's not much more than a Raspberry Pi and some I/O devices. But we weren't actually using Logisim to replicate that. We were using Logisim to study data path and control. But with COVID and switched to online, we managed to replicate all of that. So more or less the same labs could be carried out all through the simulation, except it took 15 minutes instead of just a second.
Interesting. Nice. So I guess this is a question for you, but then also for our other presenters. To what extent can your tools be replicated easily by students in the class, say on their own computers, which may be diverse operating systems, etc.?
If I can go ahead with that, it was a lot of effort to have this one unified setup for ranging from Mac OS, Linux, Windows, whatever the students may be using, to the computers in the lab, and having it doesn't work on my computer issue nightmare throughout the semester. I myself developed a few scripts that would download the tools, set up all the paths and do the necessary things. It was a real challenge to get it working under Windows. I had to go into Windows and then the Windows subsystem for Linux, and then some of the things were installed on the Windows side, so we would go back out, and at the end it worked out. But the second aspect was I wanted to have all the students using a real IDE, not just command line or some educational tool that they will never use again. So I took some time to come up with some scripts that would generate the necessary Eclipse project files. Eclipse is notoriously difficult to use and set up, and you have your cross tools, you have your debugger, you have your remote debugging facilities, the emulator, and so on. It's too much for students to set up. So I set up some scripts that create a project, a throwaway project with all the necessary config files and the run or debug configurations in them, and with some make files that would generate, when they click run, they would compile their assembly into binary, into a file that could be then read by Logisim, and they could just click run and simulate it on the emulate it or run it on the physical hardware.
Thank you. And perhaps the other authors
I could
Bruce,
say in terms of RIPES, so that has been a big focus that for me, I'm looking forward to the day when RIPES can be run in a browser, because that to me is the ideal thing where you can just open a tab and it just works. So RIPES, you can just download it. There's pre-built binaries for Mac, Windows, and Linux, and it should just work out of the box. If you want to use compiler support, you have to download a tool chain on the side. But the whole idea is that it's a fully sort of integrated environment that you just pop and go. Because I've seen this frustration myself, and also when I was starting out in the field, you know, when you're not a ninja with a command line, these things can sometimes frustrate you a little bit, right? And you just kind of want to get into the teaching and the learning, and so that has been a big focus for RIPES.
Thank you, Morten. Stefan?
Yeah, I have to be honest, I'm a little bit cheap. At our faculty, we give them a virtual machine with Linux inside, and everything just runs out of the box. And sometimes they try to replicate it on Windows. Mac works pretty well, but on Windows, it's a lot of pain, I believe. Like RIPES works, for example, like they just start with RIPES and then they switch to the virtual machine. In the moment, it becomes obvious that it's a better choice. But they use it in multiple courses in parallel, so it's for them it's a natural given. So they have to live with it.
Thanks. And so Ryan, you said you had 2,000 students. That seems like potentially challenging to support.
Yeah, supporting anything is difficult with that many people. But the flow we have, it works on Linux, it works on Mac. I don't think it's possible to get to work on Windows because of Yosis. I think it would be very difficult. But all students do have, access into our instructional computing cluster, and we generally ask students to just use those for their projects to avoid a lot of these compatibility issues. So if we wanted to make this more student-facing, I think it would be fairly easy for all students to access it, and we could even pre-install most of those things for them on the Hive machines.
Yeah. Thank you. So with another question from Ritvik. We'd like to ask him, as you're going about QEMU patches. I think this is maybe to Mehmet.
Yeah, I was just typing an answer. So he was asking about the LCD module, if we can really emulate that in QEMU. I was saying that there are some patches I've seen about adding that support to QEMU, but I was not able to use that. We just stop before the I/O. We actually, put breakpoints into the memory I/O operations and view the peripheral registers. So there are some panes you can set up in Eclipse that would show you the contents of I/O registers. I don't remember was it an SVD file? So there are some ARM specific formats, some XML file describing the peripherals of an SoC. So if you load that into Eclipse, it shows you nicely what are the input output registers and what are their states and what are the individual bit fields inside them. And you can, watch their changes. You can put breakpoints that break when those values change. So we've been using that, but not to a great extent, I should say.
Any follow-up? Yeah, please go ahead.
Yeah, so I guess I was thinking, I had like a little bit of experience with this in undergrad, and so like what we use like a totally different IDE. We use like some TI board and we use like Kyle Microvision, but we had this LCD lab. And we had two phases. And the first phase was you write the software. You have to like fill in some driver stuff and then implement something that just sends pictures and text out. And we had like an sort of emulator built in that I think they custom built for this. And what it would do is it would just emulate the screen itself. You didn't have to, you did like, I guess, have to specify the connections, like what registers are going to this LCD, but it wasn't like wiring up a breadboard like how Logisim does. And the nice thing is that the first phase, we could just make sure, are we calling the right library function, sending the right stuff? And if we see the picture, and then we go to the real breadboard, plug everything, wired it up, and then see does the actual LCD respond, and if then there's something wrong, then you get out like logic analyzer or something, and then just make sure the wires. So like kind of not like it was just like a good way to sort of test that we can interface with hardware correctly if we had ideal circuits and ideal hardware components. And then so I was wondering if sort of there was something like that. So like you run QEMU and then like some pop-up window comes and it shows an LCD character display, or you know, shows push buttons, and then when I push it, will it say hello and that kind of thing.
Yeah, I've seen some I think there's an Eclipse fork for embedded development, particularly for ARM devices that have this ability to, you know, put the pictures of the boards, put the peripherals up there, and actually emulate the behavior of LEDs and LCDs and so on. That wasn't available for the single board computer that we went for, Raspberry Pi. There's no reason it wouldn't be possible, you know, but that's not what people in that community are using. They're using devices that are only work as I don't know if there's a better word for it, as slaves to a computer that are programmed through the USB, and they don't work on their own. Single board computers, they boot their own software, so they are not falling into their description of a device. We were using them just as the slave peripherals, peripheral boards. So if we went for ARM 32-bit architecture, I believe what you were describing could be used exactly in the, I think it's called GNU MCU, if I'm not mistaken. That's the IDE that supports all of these features. And they have a QEMU fork with all the board emulations.
Awesome, thank you.
Okay. Thanks to all of our presenters and to all of you asking questions. Really appreciate it. It is 1:05, so we have our 10-minute lunch break now, depending on where you are. Maybe breakfast or midnight snack. But so in 10 minutes, 1:15, in 10 minutes, we will be having the next session on architectures.
Thank you.
See you there.
Thank you.